I would like to start by thanking the organizers for this conference. I know that they have been doing a lot of work, and I just want to say that I'm really happy to be here in this beautiful land and this beautiful historical observatory. So thank you very much for everything. So yes, today I'm gonna, as we already see, we're gonna have hopefully finally the Euclid observations, and I'm gonna discuss about how we're preparing, how to actually take advantage of these observations. I just want to say that this work wouldn't have been able to be done without the extreme help from Christophe Hollard, Etienne Bachelet, and of course my PhD supervisors, Andrew Cole and Jean-Philippe Poliot. And I don't know how to use technology. And of course, these observations will have been made without the hard work of a few lot of people over the last almost 2 decades, work that has been published and unpublished. So I want to thank them all for this. And of course, I want to thank ESA and the Euclid Consortium for getting on board with this. And hopefully they will enjoy the results of this first collaboration, and they will want to have even more. So having the Euclid observations, it's very important for multiple reasons. It will give us a first glimpse of how the Roman fields would look like, but also it's very important because it will give us a chance to have precise mass measurement of the Roman events from even the first year of the Roman survey. And why is this important? Because as we know from the light curve alone of the microlensing events, we get the mass ratio and not actually the mass of the host star and the planet. And that's a problem because most of the demographic models, they use the mass function. As a result, a lot of people in the exoplanet community, they don't really agree with what we're seeing, also because microlensing can probe space parameters that other detection techniques can't. So as a result, a lot of microlensers will get the question, do you really believe that the Sub-Saharan desert doesn't exist? And, it's a very religious question for some people. So, and also as we have seen these last days, we also have a lot of inconsistencies about the mass function inside the microlensing community, depending which survey we are talking with. So all these inconsistencies will be solved with a large number of microlensing events and also with precise mass measurements. So the large number will come hopefully with Roman, which is expected to detect more than 1,000 exoplanet events via microlensing, which is very exciting but also very scary. But unfortunately, Roman cannot have a accurate mass measurement alone. It needs the help from other space-based or ground-based observations. And we can have a mass measurement with the microlensing parallels, so basically having two telescopes with large distances observing at the same time, but also we can do it with follow-up observations. So Dave showed a lot of examples of follow-up observations that we have done with KEC and HST. And why do we do this? Because we really want to resolve the sourcing lengths, and this will give us the relative proper motion and also constraints about the angular Einstein radius. And as a result, we will have a very, very precise mass and distance measurement. So this is what we expect to have with Euclid, but not follow-up, but pre-follow-up, so we will observe the frames before the actual alignment. But it's not all easy-peasy. So these are the simulations that were presented in the Bachelet 2022 paper. These are simulations made by Matthew Penny. So what he did was simulate Euclid frames, observations of the Roman fields 5 years before the Roman launch. So here I made a time frame. So as you can see, this is the simulated first Euclid epoch, and these are the moment of alignment for each event simulated inside these fields. And here we have the separation depending on the relative, depending on the relative proper motion. Don't ask me why this is like that. This is Matthew Penny's way of simulating things. But the important thing is that if we take into account this Euclid epoch, we will expect to have up to 200 milliarc-second separations in the Euclid fields. Unfortunately, because of various reasons, we didn't make this deadline. So this is the real Euclid epoch. And as you can see, we go down to 140 milliarc-seconds at best. And let me remind you that Euclid is not K. K has a 10 milliarc-second, less than 10 milliarc-second pixel scale. Euclid is 100 plus, which means that basically all the events will be inside 1 pixel. Good fun. And hopefully with oversampling, we will be able to go down to, I don't know, maybe 30 milliarc-seconds, but still, this is a very challenging thing. And we really, really want to make the most out of these observations. So to do this, we really need a tool specialized in fitting through some lens parameters. So basically, their separation and their fluxes and their orientation. So the last year and a half, I have been working on a tool that can do exactly this, fit the source lens separation, fluxes, and orientation. It is based on a method created by Christophe Allard. It has already been used in 2 microlensing follow-up events, one including Joshua Blackman's white dwarf. I named the pipeline ESA after my grandma, who passed away about a year ago in Greece while I was in Tasmania working. And I had to come up with a name for the pipeline, and that was the best name I could think of. I think that the method is described in one of these papers, but it was written by Christophe Allard, so maybe it's not really made for the common reader to understand. But it's very simple, to be honest. So here we have the 2 stars, the bright star and the fainter star. And what we do is calculate the photocenter, which obviously is not there, but I tried to exaggerate a little bit the distance to make the plot more clear. So we have the photocenter, and then what we do is basically calculate the distance of the 2 stars from the photocenter. So the code will fit the photocenter coordinates, the total flux between the 2 stars, the total flux ratio, the distance between the 2 stars, and the theta, which is the orientation between the line that starts from the bright star towards the faint star and the x-axis of the photocenter. This is very important because this is how we will basically know, this is how we will basically know which star is the faint star, which star is the not faint star, less faint star. Okay, I'm running late. So how it works, basically you have your image, you find hopefully your target, you make a subframe of your target, then we do a skybar count estimate. I'm doing this using the same method in source abstractor, and then we create another subframe with the photocenter where we will calculate the estimates for the photocenter and total flux of the source and lens. Then the code will fit the photocenter coordinates and total flux and skybar count for a grid for the separation, total flux ratio, and the orientation. The grid is dependent on the user. Once we have the best fit solution, then the code will fit the whole 7 parameters, and it will do this until it converges. If it converges very far away, maybe you want to check, go back. Finally, the code will use an MCMC to derive the parameter distributions. Just a few characteristics. I'm using Dunhill-Siffel's method for the chi-square minimalization. It's written in C wrapped in Python. I use a clean architecture, which makes it very adaptable. So you can add many use cases. It takes seconds to minutes to run without the MCMC. and it also provides unit test and use cases test. So to test the code, I did Switzerland simulation frames using photoutills. I tried to simulate the V's instrument criteria, and I created simulations using different Switzerland separations and total flux ratios. So these are the preliminary results. Here we have the, I'm using pixels and not milliarc seconds because we don't know how many milliarc seconds will be inside each pixel. So we have basically the real distance minus the fixed distance divided by the real distance. So as you can see, for most of the events from 5 to 1 pixel, we will have basically 10% accuracy. The breakpoint that you see here, it's because when I was fitting these, in the beginning, I was using bilinear interpolation and not cubic spline interpolation. That's because it was going faster. And I realized this last night, so I didn't have time. I wasn't in a good state to actually redo the simulations. Apologies for that. But I think it's safe to say that, you know, it will follow this perfect almost zero line. The point here is that once we are inside the 1 pixel, as you can see, the code starts to lose its accuracy, and then we reach the 0.4 where it really breaks. And it breaks there because actually there are a lot of degeneracies. So I'm making a chi-square map to see how many solutions I get. And basically there are a lot, not a lot, but a lot of times there are multiple solutions for the same low chi-square. This is something that we can solve partly with knowing the source flux, so we can constrain these, but mostly this will be solved if we have multicolor observations. So it's very, very sad that we will not be able to have the NISP instrument, but hopefully with Roman we will be able to reobserve. Once we reobserve these fields, we will have multicolor, and then I'm not sure how low we can go because I haven't run all the tests for that, but hopefully we will be able to have very precise mass distance measurements for down to 0.2 pixels. And here are the total flux ratio also. As you can see, the lower we go, the more the code starts to lose. There are more degeneracies that occur. So the next steps are to work on the PSF model in Euclid. I know that there are a lot of people from the Euclid consortium and also from microlensing that there are much more experts on this than me. I'm also going to try different numerical fitting methods and interpolation methods, hoping that maybe this will solve some of the degeneracies. And we'll also finish the PSF model function. That's for the ground-based observations. So this code will be used also for ground-based instruments with adaptive optics. And once this is done, it will be an open source code. And also there will be a paper coming out soon with real results. And the takeaway notes are that we will be able to have 10% accuracy in blending separation and flux ratio for down to 1 pixel. We need multiple observations for less than 0.8 pixels. We will be able to have follow-up on all potential events in the Euclid and Roman fields. I have also tested in Roman fields, but I was very tired yesterday to actually add these. But I must say that these are good, but we also need microlensing parallax. So I really hope that more people from ESA, China, or I don't know which other continent will be willing to join the hunt and explore these beautiful unseen worlds that surround us. Thank you.
Okay, maybe just one quick question. But we have many questions. Let's see. So the first thing I would like to ask, so in your simulation, you're using provided PSF. So you're not going.
Yes, it's the PSF from the Euclid simulation.
Exactly.
Yes.
Exactly. So, would you gain something if your tool would be also able to make a retrospective PSF from real images? So, when you're going to face real images, maybe the modern PSF would not be accurate enough and then you need to reconstruct a PSF from nearby as with the stars, perhaps. Maybe that would improve.
I have a function that does a PSF model. I kind of follow how stretching does it in the airport. So I have a function that does empirical PSF model, and I have a function that does analytical PSF model. I haven't finished combining the two and also validating this. But it's gonna be part of this. I don't know how helpful it will be for Euclid PSF. I have not worked on this. This is something that will happen later in the year. But yes, I'm open to all things. And this is why I did this code in a clean architecture, so you can add as many functions, as many things you want, and it's very easy to adapt.